Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Hopefully you guys are doing well. So announcements, I guess, before we begin. So I just sent out an email a few minutes ago about the study hall session. So it's actually going to be tomorrow at 2:30. Seems like it's when most people can do it. So that's what we will do. Something else I do also want to remind you guys is just of the schedule. So you guys know you have like a quiz or a test every week, so that's not anything special. But I do want to emphasize that you guys should start around now paying attention to how your finals are laid out. To that end, I did send an email a couple weeks ago about the final exam schedule and where your final is. If you lost that email, you don't remember the link or whatever, I just want to show you here as you're seeing my browser. You can actually just Google Fordham final exam schedule. If you go into that link here, you'll see here the fall 2020. It says preliminary because they want to be able to, oh, maybe I'm logged in under a different thing. But normally you'll see here the schedule. It's going to be right there. So make sure you actually do know how to actually do that. Yeah, so I don't know, why am I logged in into the other one? This is weird. I thought I was logged in with my
I just have a quick. Is this study hall mandatory? Just because I have a class at 2:30, so I won't be able to.
It's not mandatory, but it's supposed to be it's supposed to be helpful.
Okay, because it ends at like 3:45, so I can make like the second half of it, I think.
Okay. Let's see.
Will the study hall be recorded?
I will, yes. However, of course, if you can show up in person, that would actually be the best outcome, I think. I don't know. Maybe my cookies are messed up or something. I'll worry about it later. Anyway, so yeah, be sure to check when your final exam is here. It's not letting me in because I'm signed into my other Gmail account. Yeah, go there, make sure you know when our final is, make sure you know when the finals for your other classes are. You do want to start planning out your final exam week as well as other exam weeks. So just make sure you know the schedule because, and I'll talk about that I think tomorrow as well. Yeah, that being said, I think that's all I wanted to say. Let's actually pick up with where we left off. I actually have some cool things to show you guys today. At least I think they're cool. Hopefully you think they're cool as well. So a couple cool things, maybe even 3 cool things, depending on how far we get. But it should be rather interesting. So I left you guys off with some problems to do last time. Hopefully you took a crack at those. We're actually going to look at those now. Just to do a small recap, we've been talking about things called power series. This is what they look like. And when you expand them, they look like that. Essentially, they seem to be a model for something called like a polynomial of infinite degree. Whereas, do we even know if that would even make sense, such an object? Is it even useful? Does it actually make mathematical sense? It turns out that in our sense of convergence, it does make sense. In fact, it will always make sense. It's just a matter of where. So it's possible that such a series, a power series, will converge only at a specific point, or it will converge for all real values of x that you can plug in, or it will converge on some interval of finite length with radius big R. And this radius is called the radius of convergence. Then the interval can be expressed in this form. And when you actually expand it, this is essentially what it would look like. Notice that the endpoints may or may not be included. These are things that you would have to check for in addition to that. Okay. So we take the convention that R equals 0 would mean that it only converges at one point, namely x equals x naught. R equals infinity would mean that it converges for all x. And R equals any other finite value. We call that the radius of convergence. Right? So those are some pictures here. How do you find the radius of convergence and interval of convergence? Always the ratio test. Always going to be the ratio test in this class, right? It's not always in general, but in a Cal 2 class, it's always the ratio test. Okay, so we actually did an example where we wanted to find the radius of convergence and interval of convergence of this problem here. The series as n goes from 0 to infinity of x to the n. This is a power series. In fact, you can think of it as a power series where your coefficients are given by the sequence function 1, and you're centered at x equals 0. Just to illustrate what it might mean to make sense, that idea is, if you plug in certain x values, you realize that you'll generate a series, and then you want to know that that series actually makes sense. Okay, we saw that not all x values made sense in this particular series, and so we wanted to find the specific set of x values that would make sense in this series. So we did the ratio test. We saw that we need x values to be between -1 and 1, strictly speaking. However, we do need to check the endpoints. So we did that. And we realized that at the endpoints, it actually diverged. So it turns out the interval of convergence was actually the open interval from -1 to 1, which means that your radius of convergence is just 1, which, as you can see here, is half the length of the interval. And we just did that by the ratio test. So nothing really new to learn here. We're just using something that we already know about to answer a certain sort of question. Okay. Then I ask you, what does this converge to, which is hint, hint, because earlier in the lecture, I mentioned about strategies for computing series. And I also mentioned if I ask you what a series converges to, chances are it's going to be geometric. And here it did end up being geometric. And so we know how that converges to a over 1 minus r. And essentially, basically what we're saying is this infinite series, this power series is equal to this function, at least when our x is between -1 and 1 inclusive. And I do mean that as a bona fide equality. These two things are one and the same. You can think of the left side as just another way of writing the right side. Kind of like if someone wrote 0.5 and someone else wrote a half. You literally wrote the same thing, you just wrote it in a different version. Here, we have an infinitely long way of writing out this function, right? But these two guys are equal. They are equal on this. So on this branch right here of the function 1 over 1 minus x, the series x to the n describes that function in all its details. Like there's no difference between the two, right? This is an idea that we're going to be using today and we're going to be using moving on into the future, okay? So I ask you to repeat finding the radius and interval of convergence of these two. Hopefully you actually tried that. Let's actually get through those, okay? So here is the guy here. So we start here on 11/5/2020. Okay, all right. So we want to find the radius of convergence and interval of convergence. What do we do?
Ratio test.
Ratio test. Say it with a lot of excitement there. So we employ the ratio test. Always the ratio test for this sort of question. And so essentially, we're going to compute the limit, and of course it's always as n approaches infinity, of I'm going to plug in n plus 1 everywhere, and then flip and multiply by the original an. What we would get here, notice that we can rearrange this. This is 2 to the n over 2n plus over 2n plus 2. And this here is x minus 4 to the n plus 1 over x minus 4 to the n. That parenthesis looks a little bit straight. Let's actually work on that. Okay. So now notice that this here will cancel that. So that's just your x minus 4. And now we can actually just take the limit. What is the limit of this as n approaches infinity?
1.
It's 1, right? So this goes off to 1, which means overall my limit now just becomes x minus 4. And then what I do is I set this less than 1 for convergence, because that's what the ratio test says. And so that automatically gives me an interval. So this means minus 1 between x minus 4 and 1. And I can add 4 to both sides. And so I have the interval where it converges absolutely is strictly between 3 and 5. Now, again, we always check the endpoints because we don't know if things can work at the endpoints. So we're going to check endpoints. So if our x were 3, what would happen? Well, you go to the original series and you plug in x equals 3, right? So if x were 3, you'd actually have minus 1 to the n over 2n. It's actually n goes from 1, right? Yeah. Now tell me about that. Converges or diverges?
Converges, but not absolutely.
Right? Which converges by, how do you know?
Alternating series test.
Right, by alternating series test. So it's not absolute convergence, but it is some sort of convergence. So the endpoint will work in some sense. Then now you plug in x equals 5, right? So I go here, plug in x equals 5. 5 minus 4 is 1. 1 to the n is 1. So then at that point, the series becomes n equals 1 to infinity. And here you just have 1 over 2 to the n, which converges or diverges?
Diverges.
How do you know?
You can compare it to the, is it harmonic series?
Right. It is harmonic. It is harmonic. Right? You can factor out the 1/2. It's literally the sum of 1 over n, right? It is harmonic. It's literally a constant times the harmonic. And so we can talk about the interval of convergence, right? So the interval of convergence, it's between 3 and 5. However, 3 may be included. We do have some convergence there. So it includes 3, but it does not include 5. That is our interval of convergence. These are the set of x values in which this guy will make some sort of mathematical sense. Now, of course, there are tons of ways you can find the radius of convergence here, but you can, of course, use a picture to tell you, right? So your radius of convergence, notice that this is centered at 4. You just want the distance between 4 and 5. So again, radius of convergence is 1. Another way you can do it is just do b minus a over 2, 5 minus 3 over 2, whatever you'll get. B minus a is just the length of the interval. And you just want half the length of that interval. And so your radius of convergence here is 1. And hopefully you guys got that as the answer. But that's the answer. That's how that's going to look. Any questions on that? We're gonna move these down. Okay, so here's another example. Same thing, want to find the radius and interval of convergence. So we're just going to go in, use the ratio test. So our L here is going to be the limit as x to the n plus 1 over n plus 1 factorial. This is n factorial over x to the n. And this here cancels that. And so this here is going to be the limit of n factorial over n plus 1 factorial. And then I'll just have an x hanging out here. Tell me about that limit. How do I find that limit?
Rewrite as n plus 1 times n factorial, and the n factorials cancel in the numerator.
Right.
Denominator.
The n factorials are going to cancel. And so got kicked out. Let me let them back in. And so this is really just the limit of 1 over n plus 1 times x. All right. What is that limit?
Zero.
0. Now it turns out that 0 is less than 1 always. Right? So no matter what x is. So here I'm in a situation where no matter what xi I plug in, this limit is going to give me something that's less than 1, which means this guy converges everywhere. And which also means, therefore, the radius of convergence is infinite. Right? It'll converge for all x. Okay. And so, yeah, that's basically it. That's how you go and you can test, find the interval of convergence and the radius of convergence for some power series. Always the ratio test, and then it's just a little bit of arithmetic. Okay, so hopefully that's fine. Okay, now here's something else I want to do. So this is to go back. Maybe I'll just write it here. Recall the function 1 over 1 minus x could be represented by the series x to the n if our x was in -1 to 1. Okay, let's capitalize on this. Okay, so I accidentally discovered a way that I could rewrite this particular function in a particular way, right? I can look at the function 1 over 1 minus x as just the sum of a geometric series where my a is 1 and my r is x. And so it really was a way that I could actually write an infinite series to represent a function on a certain interval. It turns out that that's super useful. And that actually leads us into the next section where we're going to be representing functions as power series. using known power series. So essentially what we're going to do is I'm going to use this fact that I know that I can represent the function 1 over 1 minus x as that series to be able to write some other functions as series, okay? And you're going to see today, like, why would I want to do that? Well, so you might ask the question, why would I want to do that? Well, let's actually see some reasons why we want to do that. So that's what we're going to do though, right? So essentially I'm going to look at this relationship. I know that that relationship is true, right? I can think of this function as that series. Okay, now I'm going to use that fact and look at some of these other ones, right? So suppose I have functions like these. My goal is to find series representations for these guys, power series representations, okay? And my claim is that they are similar enough to 1 over 1 minus x to the point where I should be able to find series for them by using the fact that I know a series for 1 over 1 minus x. Now, similar enough, in quotes, is something that we will see how it is applied in each situation. But here is how it's applied in the first situation. So let me do one for the team. I'm going to completely do the first one. And you're going to see how we would actually go about doing this. I'll ask for your ideas on the other two. So here we go. Suppose I have this function, 1 over 3 plus x. So now I look at that, I'm like, well, I want to find a power series for this guy. I don't know a power series for 1 over 3 plus x. However, at this point, all I know is a power series for 1 over 1 minus x. So maybe what I want to do is actually to rewrite this as something that looks more like 1 over 1 minus x. So how can I actually go about doing that? Well, the first thing that's different is the 3. So I don't want a 3, I would want a 1. So what I can do there is I can just factor off the 3. And I have that. Now I start to realize, okay, so now it's starting to look more like 1 over 1 minus x. However, there's a plus in the middle. I don't want a plus in the middle. I want a minus in the middle. I want 1 over 1 minus x. So what I can do is I can write this as minus a negative, right? And so now what you see me have is this actually looks a lot like 1 over 1 minus x. Notice here that if I do something like let x, let me do a fancy x or a big capital X. If I let x equals minus x over 3, notice that what I have here is 1/3 times 1 over 1 minus that fancy x, right? It's just that now my x is replaced by minus x over 3. But it's just another variable, like x is a variable. So essentially what I'm going to do is I'm going to just think of this as a series, right? So this I can actually replace with a series. I know that the x to the n is what that guy would be equal to. And so similarly, I can rewrite this guy. So this guy I can rewrite as 1/3 the series of the x to the n. Here my n goes from 0 to infinity. Or we could think of this, because again, we can actually think of this as geometric. We could think of this as geometric with a equals 1. Let me be specific as what I'm thinking of. We could think of 1 over 1 minus x over 3 as the sum of a geometric series with a equals 1 and r equals minus x over 3. Okay. Either way, I would be able to write it as a series in this form, right? So it's the A times R to the N. Okay. I can actually clean this up a little bit. Let me do that. I can distribute the N, so it's -1 to the N, X to the N over 3 to the N. And in fact, I can even move that 3 on the inside. So this looks like -1 to the N, X to the N over 3 to the N plus 1. And notice that here, this is a power series. So this here, power series. How do I know it's a power series? It fits the definition. My Cn is -1 to the N over 3 to the N plus 1, and my X naught is 0. And then if you go to the original definition I gave you, that fits. So power series is anything that looks like this. If I write my Cn as -1 to the N over 3 to the N plus 1, plug in 0 in this position, I actually get exactly the series that I just had, right? So this is a power series. And so now I might ask the question, where does this work? Now, we could do the ratio test. But it is geometric, so we know how to actually what it is, but it is geometric. So we could just know that the radius of convergence is going to be where your R, which in this case was -x over 3, is less than 1 in absolute value, right? So this basically means -1 is less than x over 3, greater than that. And so my x is going to be between -3 and 3. Okay. Now, we do want to check the endpoints. Check endpoints. So I would go in, if I plug in x equals -3, what would happen? Plug in a -3 here. Okay, so I can think of it as plugging in a -3 here, right? I would actually get that guy. Notice that this would give me that's -1 to the 2n. That's it, just -1 to the 2n, right? The 3 to the n's would cancel. And so diverges by test for divergence. Similarly, if my x equals 3, I would actually get the series of just -1 to the n. Again, diverges by test for divergence. And And so essentially what this means is this function, I can write it as a series. Which series? This series. And that is going to work for x between -3 and 3. Okay. Any questions on that, on this process?
Yeah, why is the summation from 0 to infinity?
It was always from 0 to infinity.
Is that just the definition of our power series?
We found that, but yes, a power series should start at 0. But that was in the original description. Yeah, so this was this guy.
Okay.
Right? So yeah. And this one here, so there was one here that I gave you in the example where it started at 1. How you can think of that is it is a power series, but let your C0 term be 0, right? So you could think of it that way, right? So if your power series doesn't start at n equals 0, you can think of it as a power series where all the terms up until the n value that gets started, the function assigns those as values 0 and then starts assigning non-zero values after. Okay.
Would it make a difference if when you're checking, oh, sorry.
Yeah, go ahead.
Would it make a difference for when you're checking the endpoints if you plugged it into the series when you distributed the 1/3? So it ended up being like 3 n plus 1 in the denominator.
No.
Okay.
In that case, you would have just gotten -1 to the n over 3. And that still diverges by test for divergence. Right? Like you'd have a third of whatever answer you got, but a third of something that's not 0 is also not 0. So it won't make a difference.
Okay, thank you.
Okay. Yeah. So that's how we would find this one. So I can actually write that as a series. Okay. Now let's move on to the other ones. I want to write this one as a series. Okay. So it was like the other one, except I squared the denominator. Okay. So now you would say, well, I know how to write 1 over 3 plus x as a series. So here's a common thing that a student would do, but probably not work. Common first approach would be to think of this as 1 over 3 plus x times 1 over 3 plus x, then write each of these individually as a series of blah. But it turns out actually multiplying that out and regrouping, it would be difficult, very strenuous. To actually multiply out, regroup like terms, then you have to come up with a formula that describes all the terms. It's probably not the way you want to go about it. So now, so aside from the obvious, just do the multiplication. Can you think of some other way that 1 over 3 plus x all squared relates to 1 over 3 plus x? Any relationship.
Could you repeat the question?
Find a relationship between 1 over 3 plus x and 1 over 3 plus x all squared. Other
Wouldn't
than
that
this
be part of-
multiplication relationship.
Um,
Yeah?
First thing that came to my mind is when we did the partial fractions and like the decomposition part. I don't know if that's right though.
Right. So this would look like something like a over 3 plus x plus b over 3 plus x all squared. Like you wouldn't get rid of the 3 plus x all squared. Right.
Yeah.
So you'd still have that 3 plus x squared if you break this down in a partial fraction. Other relationships? Maybe I'll give you another hint. Instead of the 3 plus x, maybe the 3 plus is clouding your judgment. What if I wanted to compare 1 over x versus 1 over x squared? And you wanted some sort of relationship that connects those two, but it's not just squaring or multiplication. Can you think of anything?
One looks like the derivative, but no negative.
It's like the derivative, but no negative. Right. Notice if I took the derivative of this, I would actually get the negative of that. But in other words, I could actually move the negative derivative over here. I can say the relationship is the negative derivative. Luckily, we're in a calculus class, so this is a bona fide relationship that we know about. So here's a better relationship to use. Now, it turns out using the derivative relationship between the two is going to actually be better. So what you would notice here, note, if I were to take the negative derivative, or let me write it the other way, 1 over 3 plus x all squared. This is actually just the negative of the derivative of 1 over 3 plus x. Right? Agreed? Yeah, that works. Okay, so now, however, I do know how to write 1 over 3 plus x as a series. We did that earlier. So I know that that is true. So this, so this is that by part A. And so now here's what I'm going to do. I am going to do the following. I'm going to take this to mean the sum of the derivatives. Now, we will pause here and I will ask you, why is that legal? So we do know that the derivative of a sum is the sum of derivatives. However, we have an infinite sum here, and we know that infinite sums can actually mess things up. I claim that this is actually the same. I can take the derivative of the infinite sum, or I can take the infinite sum of the derivatives. Why am I allowed to do this? Ideas?
Would it follow the same principle, like how limits can be distributed into series, or like as part of the properties of series?
No, it wasn't a property of series. We had two properties of series, and that was you can factor constants out and series distribute across sums. So we didn't have any properties of series that were directly related to calculus. Well, there was something that I told you that, okay, why this thing is important is because we're going to want to do calculus eventually. You remember when I said that?
You say that a lot.
I do say that a lot, but in the context of infinite series specifically.
Does it have to do with absolute convergence?
It has to do with absolute convergence, right? So remember I mentioned conditionally convergent series, you can change their values by rearranging the sums, which means doing calculus over a sum, the answer will change depending on your arrangement. This was a problem. However, in the case of absolutely convergent series, this is not an issue. So in fact, commutative addition works for absolutely convergent series. This means that an infinite series that is absolutely convergent is a bona fide number. All the properties of arithmetic work, including the fact that I can distribute calculus across the sum. This guy does converge absolutely on this interval. How do I know that it converges absolutely on that interval? I use the ratio test to prove that it converges, and the ratio test automatically gives you absolute convergence. So the reason this is legal is because of absolute convergence. Of course, there's a window. So obviously here, I'm not thinking of my x as being outside of that window. But once my x is inside of that window, that's allowed. Derivative of a sum is the sum of derivatives. The order in which I add things isn't going to matter because of absolute convergence. So because of absolute convergence, summation signs and derivative signs can be interchanged. Also, summation signs and integral signs can be interchanged. If you have conditional convergence, this is not allowed. This would be incorrect. Okay, so it's very important that you recognize that. Okay, so I can actually do this. So now all I need to do is find the series of the derivatives. Now, what is the derivative of that? Let me emphasize, it is d dx. What is the derivative?
Well, can you separate out -1 to the n over 3 to the n plus 1 as like a constant? And then
It is a
that
constant,
one,
right? Because d dx, there is no, n is not an x, n is the positive integers. This is literally just a constant, right? So this I know. And again, we knew this since Calc 1. The derivative of a constant times a function is just a constant times the derivative of the function. I'm not always going to show this step, by the way, because it is something that I would expect you to see just right away. But yeah, so now what's the derivative? Just nx to the n minus 1, right? So essentially, this now becomes minus 1 to the n times nx to the n minus 1 over 3 to the n plus 1. Now, that's actually the power series, but it doesn't look like it's in the standard form that we're used to. So I'm going to want to clean this up. First of all, I can move in the negative sign and multiply by that. So of course, we remember from laws of exponents, you add the powers. So this is -1 to the n plus 1 times nx to the n minus 1 over 3 to the n plus 1. We also learned in Calc 1 that we can shift a series by shifting the indexes. So what I can do is I can shift this. So I'm going to shift my n shifted to n plus 1 everywhere. So my old n minus 1 is going to be equal to n. Technically, to do proper etiquette, they would use a different variable here, but it's a dummy variable, so we can always swap it back. In fact, let me actually do that first. And from now on, I'm not going to do it. I would just use only n's, but you can do a shift. So you can do something like set k equals n minus 1. And then that basically would mean that so this would mean that n would be equal to k plus 1. So you go everywhere and you plug in k plus 1 in place of n. Okay. So this just becomes this minus 1 to the k plus 2, k plus 1, x to the k over 3 to the k plus 2. But now you can just swap the n's for k's. It's actually not going to matter. You'll notice that it was just equivalent to changing all n's to n plus 1. So this is just equivalent to changing all n's to n plus 1 at the step where we introduced k. Okay. So yeah, we can do that. Now, again, still not really a power series. It starts to look more, but now it starts at n equals -1. Yuck. What you can notice, though, is that if I were to plug in n equals -1, note, if we plug in n equals -1, you would have the series. Well, no, you wouldn't have the series. I'm just plugging in n equals -1. I would have -1 to the -1 plus 2 times -1 plus 1, x to the -1 over 3 to the -1 plus 2. Notice that that is going to give us 0. So the n equals -1 term does not matter. Does not matter in the sense that to plug it in is adding 0. So we can start at the next term. And so that ultimately gives us the power series. So it's going to be -1 to the n plus 2, n plus 1, x to the n over 3 to the n plus 2. And again, this is going to be true for x between -3 and 3. Notice that if I plug in, oh, is this going to be true for that? So we know it's true for -3 and 3. So check endpoints. So if I plug in x equals 3, I would have the series of -1 to the n plus 2, n plus 1, 3 to the n over 3 to the n times 9. These guys would cancel and this diverges. And similarly, if I plug in -3, it would also diverge. So this does work for x in that open interval -3 to 3. Okay. So that's that one. Okay, so we can actually use a relationship where we can modify things algebraically, like factoring things off, rewriting things, writing a plus as a negative of a negative, things of that sort to kind of maneuver something into a form that I know a series for, and we can get a series that way. Sometimes the relationship you want to take is actually a calculus relationship. So I see this, but I notice that it's kind of like the derivative of something that I already know a series for. So now, if that series happens to be absolutely convergent, which a power series is always going to be absolutely convergent somewhere, then I can switch these guys and I can just take the derivative of this part. Everything that's with n is a constant, so I'm just differentiating the function of x, and I can obtain a series like that. And I might have to do a little cleanup to get it in the right form. So, you know, we can have something that's a 0th term, a 1th term, a 2nd term, all the way up, right? So that's a power series for this guy. Where did I put that? That other one. Ah, here. Here's another one. Okay. Can you tell me a relationship? That compares to the first one, 1 over 3 plus x. Right,
Isn't that
so
just a derivative?
Integral.
the integral, right? This is actually the integral of 1 over 3 plus x.
without the absolute values.
Right. Yeah. It's actually still true. Okay. So now, right, because this just means because without the absolute values, I'm not allowed to plug in negatives anyway, so I don't even need the absolute values. So, and again, I know that my x ultimately is for this guy to work, my x is ultimately strictly between -3 and 3. So when my x is between there, I'm always ln'ing the same thing. So this is equivalent to an absolute value. So this is equivalent to ln of 3 plus x in absolute value if my x is in that region. Right? Because it's going to be positive. The absolute value of a positive is positive. But yes, I like that you actually noticed that you had that knee-jerk reaction. That's good. But we're fine here. It's cool. Okay? So yeah. An integral relationship is a relationship I can take advantage of. I know a series for this guy. I forgot what the series was. Let's go back up here. Where are we? Okay, so x to the n over 3 to the n plus 1. And it's -1 to the n. And again, I can switch these guys. Like I can take this, I have the integral of that, but I can actually move the sum outside and just write the integral of the sum as the sum of integrals. And why am I allowed to do that? Absolute convergence. So now I just have to integrate that. And again, this part here is just a constant as far as the integral is concerned. It's dx, right? So what I'm going to do is I'm just going to add 1 to the power, divide by the new power. So that's going to be -1 to the n, x to the n plus 1 divided by n plus 1, 3 to the n plus 1. Of course, plus c. Don't forget the plus c, it's an indefinite integral. Okay, now I'm going to do my little shifting trick. So I am going to shift all n's to n minus 1s, right? Because that way this guy is now going to become n, which is what I want to put it in the standard form of the definition. So I'm just going to, here this becomes n minus 1. Here this becomes n minus 1. Here this becomes n. Here this becomes n. Here this becomes n plus c. This is just the sum. N goes from 1 to infinity of -1 to the n minus 1, x to the n. Over n times 3 to the n plus c. Okay. Now, you might be worried about the fact that there's a plus c there, but because I know I have absolute convergence, this was, I can think of 1 over 3 plus x as the series I plugged in. This here is a bona fide equation. It's a function, it's a relationship that I can actually plug in x values into. So what I can do is I can plug in a convenient x value. To find c, plug in a convenient x value. And you might be thinking, well, what is a convenient x value here? I wouldn't want to have to deal with that series, so probably any x value that can help me get rid of that series would work. Of course, my x also has to fit between -3 and 3, so x equals 0 works, right? And it is in the interval -3 to 3. What I would do then, this means I can go in and I can plug in x equals 0. So this essentially now is the series of 0. which is 0, right? So this tells you that my C is actually ln of 3. And so this guy here is just this plus ln of 3. And you can even think of this as the C0 term if you want, right? So that's like the C0 term. Then all the C1 terms are given by this part right here. When I plug in n equals 1, I get C1, plug in n equals 2, I get C2, etc. So that extra constant there is like the C0 term. And this is my guy. Now, where does that work? So I know it works between -3 and 3. Let's check endpoints. If I plug in x equals 3, I would have the series n equals 1 to infinity of -1 to the n minus 1 of 3 to the n over n times 3 to the n. These guys would cancel. I would have the series that converge or diverge.
Diverges by divergence test.
No, converges. Why does it converge? Right, the limit of 1 over n is 0, so the test for divergence is inconclusive. This converges. Which test would you use?
Alternating series test.
Alternating series test. And if I plug in x equals -3, I would have n equals 1 to infinity. It's -1 to the n minus 1 times -1 to the n times 3 to the n over n times 3 to the n. This guy cancels. This would become a series. Adding these up, this is -1 to the 2n minus 1 over n. Now, it turns out, hopefully you recognize that 2n minus 1 is an odd number, which means that this always returns the value -1. So it looks like that. And that diverges. Since it's harmonic. So it turns out this series, the series representation actually works at 3. So here, this guy, I don't know if I'm going to want to move all of this, but let's see what I can copy here. ln of 3 plus x can be represented by this series for any x value between -3 cannot work, but 3 actually does conditionally. Notice here, of course, that also kind of makes sense because to you, ln of 6 shouldn't be a problem, but ln of 0 is definitely a problem. So the -3, it makes sense that it didn't work out. The 3, I mean, I feel like it should work out. I mean, we're right on the edge, but I mean, if I plug in x equals 3 on the left side, it makes total sense. Plugging in x equals -3 on the left side makes no sense. So this one actually works at the right endpoint. So that is the power series representation for this. Okay, so here is one of the cool things I wanted to show you so far. And here I also put a note. We're allowed to differentiate or integrate the sequence term because of absolute convergence. So that's just something I already mentioned. But here's something cool. So in our last example, I want you to actually plug in x equals 3, since I know it's conditionally convergent there, and actually see what happens. We'll see what happens. Come on, computer, did it freeze on me? Okay. Look at what happens if I plug in x equals 3. Set x equals 3. What would you get? Well, on this side, I would get ln of 6. Over here, I would get -1 to the n minus 1. And my x is 3, so the 3 to n's would cancel. I would get that plus ln of 3. What I can do here is I can move this over to that side. Of course, laws of logarithms tells us that that's just that. And what I can do is I can multiply both sides by a negative sign. So here I would have minus ln2. And on this side, and look at that. So I mentioned a couple classes ago that this guy is, notice that that's the alternating harmonic, right? I don't know. This here is the alternating harmonic. And I mentioned to you, this guy adds up to minus ln2. And of course, you're probably very skeptical, like, why would that add up to minus ln2? That doesn't even make any sense. This guy here is just a list of numbers, of rational numbers. In fact, it's -1 plus a half, minus a third, plus a fourth, minus a fifth, plus da da da. And you go on forever. And you might say, well, what does that add up to? Doesn't even make sense. Well, we know by the alternating series test that it should make sense. And in fact, it is minus ln2. And you're like, well, why would that be minus ln2? Look, we just use power series to prove that adds up to minus ln2, which is, in my view, at least, pretty amazing. It's worth a little. because when I saw this for the first time, it was pretty. So that's how he knew, right? So this guy actually adds up to minus ln of 2, and you now actually see a proof for it. So yeah, that's how we know that's minus ln 2, right? So then I told you things also like, the sum of 1 over n squared actually adds up to pi squared over 6. Like, how would you get pi squared over 6? Well, we're not going to learn in this class how to actually do that one, because you'll actually need some techniques from multivariable calculus to do that. But you could figure out that 1 over n squared, the sum of that is pi squared over 6. But yeah, so I thought that was pretty cool. And I know we're about to go over time, but I just want to take a few minutes to actually show you something else that's pretty cool, which is it's going to help you in the future because I am going to ask you questions about this later on. Of course, the above convergence is conditional, but in some very real, meaningful sense, the alternating harmonic does add up to minus ln 2, and power series tells us this. So power series are very convenient for multiple reasons. This is one of them. Here's another thing. Suppose I wanted to compute this integral. Okay, so let me just show you another situation. Now, I would mention that in theory, we do know how to compute this by hand. You can notice that the denominator is 1 plus x cubed, all cubed. You can think of that as the sum of 2 cubes. You can factor the denominator, then you can use partial fractions to break it up into little fractions. And after a lot of maneuvering, you would be able to get to an answer, probably after a lot of maneuvering. But hey, that power x to the 9th was pretty big. So then I started wondering, well, what should the answer look like? Because I know I'm going to have to check my answer eventually. So I went and let's see what Symbolab says, just so I know what I'm in for, right? And so I went to Symbolab and I typed in that integral. Okay. And, the little waiting icon came up and Symbolab was doing its work. And I was like, okay, so what's the answer? What's the answer? And Symbolab returned, boop, cannot solve. Like, okay, that's sort of weird because I can even conceive of a way to solve this by hand. However, the technology wasn't up to it. So I'm like, all right, I know Wolfram Alpha, right? So I tried Wolfram Alpha, boom. And Wolfram Alpha gave me this, right? Which you have all sorts of trig functions. You have that log. You can kind of see where the sum of cubes formula has been applied and you're breaking it up. Obviously, you're going to break this up into a bunch of fractions. Some of them, the numerator is going to be the derivative of the denominator and you're going to get logs into play. Other ones, you might have to do like some sort of trig subs, and then you end up having these sines and cosines all over the place. Anyway, it's clear that this would actually be way too messy, right? And this is just the indefinite integral. So Symbolab couldn't even compute it, right? So we literally have a very powerful technology, a lot of smart people programming this stuff, obviously, and it couldn't handle this integral. Now, yes, I could handle it by hand, but it would be a lot of work. And Wolfram Alpha kind of shows that. So I'm like, okay, originally I was concerned with this definite integral. So let me actually do that. So I go back to Wolfram Alpha and I typed in the definite integral version. And Wolfram Alpha gave me, okay, here's what your curve looks like. The area under the curve is this, 0.439285. Okay, I'm like, okay, thank you. Still don't want to do that by hand, but it's nice to know that it's possible and technology can help me. Symbolab really let me down here, but Wolfram Alpha came through. Don't give Symbolab too much grief and Wolfram Alpha too much props. I have seen examples where it works vice versa. Wolfram Alpha couldn't figure out what the answer is, but Symbolab could. So with this particular integral, however Symbolab computes integrals, just can't handle this one. Wolfram Alpha could handle it though. But here's what I propose. There's actually a better way. And remember I was talking about last time the importance of approximations. So let's say I wanted to do this by hand. I don't have a calculator, or let's just pretend We live in a world where there was no Wolfram Alpha. The only mathematical technology of the day is Symbolab. This is a problem that is hitherto unsolved because technology can't handle it, right? So now I'm going to show you that by hand, I could find this definite integral and I can actually get it with relative ease, not by going through the route of factoring and breaking it up into partial fractions and all that, but by using series. So here's what we're going to do. So let's figure out what Symbolab couldn't, right? So this is the second cool thing I wanted to show you. And it's not going to take a long time. I know I'm a little bit over time already. But hopefully you're finding this interesting. So what I would do is I would realize, well, this guy, I can write it as x times 1 over 1 plus x to the 9th. And then that guy, I realize, well, I can write this as 1 over 1 minus a minus x to the 9th. And then I'm like, hey, that looks like 1 over 1 minus x. I know a series for that. There's an app for that. So this I can actually replace by a series of x to the n. So it's x to the 9th to the n. So this here, of course, that's x. Let me bring the x inside. It's a series, so I can bring x in and out. It's a constant as far as the series is concerned. Let's clean this up. This is minus 1 to the n and x to the 9n. Of course, I can write that as x to the 9n plus 1, and I can switch the series and the integral. I can do that because of absolute convergence. And I know that this guy here is equal to that guy. Okay. So now I can just do my integration. And that is going to be minus 1 to the n. I would add 1 to the power, 9n plus 2 over 9n plus 2. Of course, this is between 0 and 1. If I plug in 0, it disappears. If I plug in 1 for x, it just gives me the series of that. That is the integral, right? I actually computed it by hand. Now, yes, I wrote it as a series, right? So at this point, you might say, well, that's kind of cheating. That's not really an answer, but no, it's an answer. In fact, it's an answer that I can approximate to any desired degree of accuracy. How do I know? It's an alternating series. Last time I told you a way that we can actually approximate the alternating series with something called the alternating series approximation theorem. We can approximate this to any desired degree of accuracy. Right? So the integral is, right? So if I were to plug in n equals 0, I would get a half. Plug in n equals 1, I would get minus 1 over 11. Plug in n equals 2, I would get 1 over 20, etc. Right? Da, da, da. Right? So it's an infinite sum, but it's alternating. I know I can approximate this to any desired degree of accuracy. So for example, if I wanted to be able to find Wolfram's answer, all I need to do is use the alternating series approximation theorem to get my an plus 1 term to be less than 0.00006. And conceivably, I could do this, but I probably wouldn't want to do it. But in theory, I could do it. In fact, if I lived in a world where the only technology was Symbolab and Symbolab was stuck, what I would do as the human being is to work this out, and then I can have Symbolab just compute that series. Symbolab will be able to compute that series. Arithmetic, computers are very good at arithmetic. It will definitely be able to compute that to within any desired degree of accuracy. So while the software by itself couldn't figure it out, using what we know, that what we've learned in this class, we can figure it out, right? And so I just have in words here some of the things I mentioned, and I just wanted to make some comparisons. Things misbehaving. I don't think it likes when I do that. So if I had a tolerance k, I just wanted this thing to be less than k, and I can solve for n. In case you're wondering, how many terms would I need to get of this series would I have to evaluate to get Wolfram's accuracy? It turns out that I can solve this, and I'm not going to solve it for you, but the answer is actually 111,110. So I would have to add up 111,111 terms of this series to get the answer to the level of accuracy that Wolfram gave us. However, to you, that might be a big deal, but I promise you, to a computer, it's not a big deal. Computers decades ago could do that kind of operation in a matter of seconds, right? A computer today would take less than a second to add up 100,000 terms. It's nothing, it's a joke. So it actually could get that answer. So Wolfram Alpha might have used a series version to get to that answer. I don't know, or maybe it used the fundamental theorem of calculus with that monstrosity it gave me for the answer to the indefinite integral. But that is, this is a way that I could actually do this by hand. By the way, I computed this. You only need 10 terms to get the answer accurate to 2 decimal places. And also, if I add up 2 terms, so if I take the 1/2 minus 1 over 11, the answer is actually 0.409 with just 2 terms. The actual answer, 0.439. So I can actually get within 1 decimal place accuracy. Like if I only had 1 decimal place accuracy, if that's all I cared about, I could literally just, by hand, add these 2 fractions up and I'd be good, right? Whereas, yeah, Symbolab actually couldn't handle it. And I did this experiment in a couple months ago, but even today, it hasn't been fixed. Like if you go to Symbolab, you type this integral in there right now, it won't be able to actually do it. So it'll say steps aren't supported for this, or it'll give you some sort of error message, right? So that's pretty cool, right? And it also goes to show you one of the some of the things that students complain about. Why do we have to know how to do all this stuff? Like we're in the 21st century. I can just plug stuff into a calculator. It turns out you're always going to have to know how things work, because eventually, and this is a Calc 2 problem. It's not the most complicated thing out there. So I can tell you there are problems out there that the technology cannot handle. We still need smart people who know how to build things from the ground up. And even if we're designing AI or whatever to solve certain problems, we still need people who know how to program the AI. There will always be need for people who know what's going on at the frontier, right? So this is just a small example of that. So there's a life lesson hidden in here, besides a really cool fact that I can compute something by hand that Symbolab couldn't, right? Now we're going to end there, but some of you might be asking the question, but Jhevon, we just use that one series that we know about, 1 over 1 minus x is equal to the series of x to the n. What if we had some weird function like sine of x cubed or e to the minus x squared? How do we rewrite those so that we can use the 1 over 1 minus x thing? And the answer is you don't, you wouldn't. But I'm glad you asked. The next section is going to deal with situations like that. What if I don't know a power series that kind of looks like a function that I care about, that I want to do something like to find an integral or a derivative? How do I go about getting power series into the mix? That is a discussion for next time. So we'll end there. Hopefully you thought that was cool, that we can do things that the computer overlords can't, as well as you thought this was cool. But yeah, we're going to wrap up there. I will see you guys tomorrow, it seems. So I sent you guys the Zoom link. That being said, we will end there. Thank you for your time and attention and participation. Hopefully you guys have a good week, and hopefully you guys can make it tomorrow. If you can't, I'll record it. So, I mean, you'll get some information after the fact. But yeah, have a good night, everyone. And I will see you guys in the next one.